So I don't know. Maybe you didn't. I think it came out in 2005. I'm not sure.
This is
No,
a new one that came out in like 2016.
didn't watch H2O. But that movie, even though it's about mermaids, it really shows you a lot about the properties of water and how it affects nature around it. So I left this slide blank because I wanted us to come up with a definition. We interact with water every day, and so I wanted us to write a definition of water, write a description of water. So can anybody, I'll fill it in as we go. Can anybody tell me what water is or what it means to them, or something about water that we can put here? Everybody interact with water every day. Nobody? Okay, I'll go first. Maybe we're a bit shy. Ah, yes, it's thirst quenching. It's a thirst quenching agent. It's also a clear liquid, one of the many clear liquids in the world. Water is the mother of life, is the mother of life, and it's a liquid. That's true. Water is a substance that is colorless and shapes anything. Okay, that's true as well. Just going to add these right here. And I'm just doing this randomly. Water is drinkable. Water water takes the shape of any container. That's true. Ah, yes, somebody already wrote it. Water makes up, 70% of our body. Water is a substance that's made up of hydrogen. Oh, you jump in the gun, Robin. You jump in the gun. But yeah, we use it to bathe and we use it to do all of that. So let me just jump back into the presentation. We have our definition of water. Not written down. Lenika, how do you get this off the screen? I'm not quite sure the writing. All right. So water is in us. As one of our friends shared earlier, water is 70% of our bodies. It makes up our kidneys, it makes up our heart, our brain, our liver, our skin, our blood, definitely our blood, our bones included, even though our bones are hard. Water is in there. Water is in everything in our body. All right, so we need water. Water is needed by the body for these reasons. It's needed by the brain to manufacture hormones and neurotransmitters. It reduces the body temperature by sweating and respiration. It acts as a shock absorber, meaning that whenever we get hit by something, the water, intercepts the thing and or organ so that it doesn't get damaged. It converts food to components needed for survival and digestion. It helps to deliver oxygen all over the body because oxygen is in water. Yes. Water is a major component of most body parts. It lubricates our joints, flushes out body waste and mainly urine, and allows body cells to grow, reproduce, etc. And of course, it's in our saliva, etc. So it's also all around us. So it's in us and it's all around us. So we use water for recreation. So we go to the water park, we go to the beach, we go to the river, and we see water, and we use it to cool down externally. We use it to have fun. We have water sports and all of that. For industrial use, meaning it's used in factories, to help make products like our juices. used to wash off our fruits that we put in the containers to bring to the supermarkets. It's used to make chemicals that we use in our houses to clean. So water is used in those areas as well. It's also used as an energy source. Can anybody tell me what exactly I mean when I say water is used as a source of energy? Does anything come to mind?
Hydro.
That's true, Natari. It's made up of fluids, not just water, but a majority of the fluids consist of water, like blood, plasma. Well, plasma is in blood. The gelatin in our eyes, etc. So when I say that it's an energy source, I mean that it's used for hydropower. And hydropower is basically using water or the force of water to generate electricity or power. So, for example, in Iceland, they have massive waterfalls, and they create dams. And we have dams also here in Jamaica, but we don't use it for hydropower. They use the dams, the water rushes through them and over them, and the force, the friction that is created when the water moves, for example, a windmill looking structure can generate electricity. Hydro is correct, yes. Hydropower indeed. So household uses, we all know we use it to wash, cook, and clean. We use it, we drink it and all of that. Agricultural uses, as I stated before, we use it to wash our crops. We use it to, most importantly, water our crops. We use water to water our crops, yes. Because when we put water into the soil, the minerals that are in the soil dissolve, and as a result, they can be easily taken up by the plants that we are rearing. The roots pick it up, yes, Shahana. And nature, all around. Animals live in the water. Animals get food from the water. We get food from the water. And the water is in all the states in nature. Polar ice caps are solid, and the polar bears basically live on that. Then you have fish living in the liquid state of water, and then you have water vapor that is in the air. Water vapor that contributes to clouds and all of that. So let me not jump the gun. Have you ever wondered why water is dubbed the liquid of life, and why our bodies can't just use oil or alcohol instead? It's because of water chemistry. Like, have you ever wondered why water? Why God never make us so that we can use oil? Why God never make it so that we can use alcohol? Because there are clear oils, there are clear alcohols. So why exactly water? It's definitely because of the makeup of water. So what's water chemistry? Make we dive in and discover. But firstly, for those who aren't really aware of what chemistry is, let me just break it down. If you look right in the bottom corner right there, you'll see that chemistry is a science that deals with the properties, the composition, and the structure of substances. And it's defined as elements and compounds, and the transformations they undergo. So what basically makes up water? What makes water behave like this? What as a result of its structure, what makes it do this and that, and how does it move from one state to another? That is what we'll be focusing on the water chemistry. So the chemical composition of water. So on this side, we can see hydrogen. And can anybody give me any fun facts about hydrogen? Anybody know anything about hydrogen? Dun, 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 dun.
It's cold. Hydrogen is cold.
Okay, hydrogen is a gas, and that's true. Hydrogen is also the first atomic element on the periodic table. And the periodic table, for those who don't know, it's a big chart of all the elements that we can find on Earth. So hydrogen, the hydrogen atom, helium, lithium, and all of that. Those are the atoms that we can find here on Earth, and some of them even out in outer space. So hydrogen is the first one on the periodic table, and it is a positive, it's a positive ion. When I say it's a positive ion, I mean it is positively charged. But let me jump over to oxygen before I go into what exactly I never hold your breath in outer space mean. So oxygen is the 8th atom on the periodic table. So that means it has 8 electrons on its shell. That's why it gets its position as the 8th element. Hydrogen is the first because it only has 1 electron on its shell. And in order to form water, 2 hydrogen atoms bond to 1 oxygen atom in order to form water. And in the bonding process, they do a special kind of bonding. As you can see, them kind of stuck to each other. They're close together and they're sharing. You can see the oxygen has the red balls, and the red balls we are going to call those electrons. And the hydrogens have white balls, and they are, in a sense, sharing them in order to create a molecule of water. This is called a molecule. So when more than 1 atoms come together, they form a molecule. And this is a molecule of water. So water molecules are polar. So hydrogen and oxygen share electrons in order to make water. And for the upper school students, we may have been introduced to this kind of bonding. It's called, oh, let me not jump the gun, but they share in order to ensure that their orbital is full. Let me go back to what this is. The hydrogen has 1 shell, and the shell is basically the circle, but the oxygen has 2 shells. The oxygen has 1, 2, 3, 4, 5, 6 electrons on its outer shell, and it needs 2 electrons to feel satisfied, and the hydrogen, on the other hand, only has 1 shell. So on the first shell, you only need 1 other electron. And when they share with each other, they satisfy each other. So the hydrogen down here gets the 1 electron that it needs to feel balanced, and the other hydrogen gets the other electron that it needs to feel balanced, and then everybody feels satisfied because now even the oxygen has the 2 electrons that it needs to get to feel balanced. So by sharing electrons, they are supposed to become neutral. However, because oxygen, because of the size of oxygen is bigger than hydrogen because of the number of shells it has, the number of circles that it has around the center of it. And the size of the oxygen makes it hoard all of the electrons. So oxygen, see, hydrogen have the electrons willing for share, but oxygen is like, no, I want to hug everything. I'm going to take everything and hug it upon myself. So when they share the electrons, this is called covalent bonding. And as a result, because oxygen is a hoarder, oxygen is a meanie, and wants to take up all of the electrons, it becomes slightly negative. Electrons, I must mention, are negative. So when oxygen grab up all the electron share the electrons with hydrogen, but I pull it closer to itself, it becomes more negative. And the hydrogens become more positive now because the oxygen will drag with all the negativity from it, and this fact makes the molecule polar, meaning it has a negative and a positive end. So as we can see, the oxygen side is negative slightly. This symbol means slightly, and then you have the minus, which means negative, so it's slightly negative, and then you have the hydrogen side that's slightly positive, which makes it polar. The slightly positive hydrogens are attracted to slightly negative oxygens in other molecules of water, and the bond created is called hydrogen bonds. So when there's a slightly positive charge on the hydrogen, this allows the hydrogen to be attracted to other water molecules, specifically the oxygen side, because what? The opposites attract, opposites attract. So the slightly negative oxygen on another molecule is attracted to the slightly positive hydrogen on another molecules because of opposites attract. And these bonds are responsible for how the water molecule interacts with other stuff. Basically, the properties of water. Any questions so far? Have I lost anyone at any point?
No, wish.
Okay, I'll take that as a no. Oh, I'm shipping oxygen and hydrogen. Well, they've been shipped for centuries. They've been doing their thing and stunting. They're the power couple of molecules. I'll say that. Okay, so let's go. Why is it not moving? Okay, so properties of water. So properties of water are stuff that we can observe about water. So first of all, we know the states of matter. So pure water is tasteless, odorless, and colorless, and water can occur in 3 states: ice, solid ice, liquid, what we just call water, and gas, which is vapor. So the states of matter: solid, liquid, gas. At 0 degrees Celsius and below, water exists in the form of ice. So when it's really cold, like we don't experience these temperatures in Jamaica. These kind of temperatures happen in your freezer, in your fridge, in the ice machine at KFC. Yeah, we don't experience those temperatures in Jamaica, but at 0 degrees Celsius, which is the freezing point of water, ice is formed. The solid structure of ice is of water is formed, which is ice. And then you have liquid. Above 0 degrees Celsius, but below 100 degrees Celsius, we have liquid water. So we already know this we drink every day, we bathe in. This is the form of water that we use most in our daily lives. And yeah, it's all around us in Jamaica because we have temperatures above 0 degrees Celsius and below 100 degrees Celsius. Fun fact to note, persons usually say that it exists as a liquid at room temperature, and room temperature is usually just 27 degrees Celsius. Gas, the gas form of water is vapor or steam, and it exists at specifically 99.98 degrees Celsius, but person just say 100 degrees, which is fine. And this is where water moves from the liquid state to the gas state, which is steam or vapor. So as heat is applied to the water, for example, let's start over the ice part. So this is water as ice. When heat is applied to this form of water, solid form of water, the molecules gain kinetic energy. And kinetic energy is basically the energy you get when you're moving. So right now you're sitting down, you're looking at your screen. Let's say you just have potential energy. You're not moving much, you're just stationary, you're not doing anything. But when you get up and you go to your fridge for a glass of water, you're moving now, you're kinetic. You're using kinetic energy because you're moving. So when heat is applied, the particles, the molecules in the ice start to speed up, and then it breaks the hydrogen bonds. And when this happens, it becomes water. And again, when you heat the water, any hydrogen bonds that still exist break, and then the water molecules are fully free, them can go about them business and fly in the sky. Yep, that's what happens when they become gas. So the boiling point is the temperature at which water begins to boil and move from liquid to gas. So when we start to see steam coming out of our pot when mommy is cooking or boiling the water, I should say, that's when the water has reached the boiling point, which is 100 degrees Celsius, and becomes vapor. Melting point is the point at which ice becomes liquid water through cooling. So through what? Through heat, sorry. That's a mistake. I'll edit that. So specific heat capacity, we just jumped a whole level, but I will summarize. So specific heat capacity has to do with the amount of heat that is required for a substance to change from one to 1 by 1 degree Celsius, sorry. So water is said to have a high specific heat capacity. It takes a lot of heat to move 1 gram of water up by 1 degree Celsius. So the specific heat capacity for a substance is the amount of heat needed per mass to raise the temperature of a substance by 1 degree Celsius. So water has a higher heat capacity than sand, so it requires more energy to be heated. And this is why the ocean is always cooler than the sand. So another example, when you go to the beach, you always realize that the water is never hotter than the sand. Never. It's always cooler than the sand. And that is because it takes more energy from the sun to make the water hotter than it does for the sun to make the sand hotter. And that is because the specific heat capacity of water is higher than that of sand. And that is because of how it is built, you know, the structure of water. Okay, so here's a little bit more about specific heat capacity. The water's high specific heat capacity helps to moderate daily air temperatures around large bodies of water. And water specific heat capacity is more than 4 times that of most metals. So it is harder for water to raise by 1 degree Celsius, I should say, than it is for most metals to raise by 1 degree Celsius. And you can test it out for sure. If you put a spoon on the stove and you heat it up, it's going to get hot faster than if you put water on the stove and heat it up. Even if it's a little bit of, well, depending on the ratio of water to spoon. So heat of vaporization. And I know these words look big, but it's basically saying that the amount of heat required to move 1 gram of water, liquid water, to gas. That's basically what it's saying. So water, hydrogen bonds make it difficult for water molecules to escape the liquid state and are responsible for its high heat of vaporization. So once again, it is hard for water to even get warm, and it's even harder for water to move from the liquid state to the gaseous state. And you can attribute that to the specific heat capacity of water. So the hydrogen bonds must be broken before water can evaporate, and this requires considerable energy, which we stated before. Because water has a high heat of vaporization, it helps our body and our planet to maintain our temperature within a tolerable range.
Slow down.
And we sweat, water evaporates from our skin and it cools us. Since the evaporation of water requires a considerable amount of energy, it is very effective in cooling us. So water also helps to moderate global climate by absorbing solar radiation and dissipating the heat by evaporation of the surface. So I skipped this slide and I jumped right to this one because it ties right back into the states of matter. So water exists as a solid, liquid, or gas. And also another form that has been recently discovered by scientists, but I'll leave that for the end. So latent heat of fusion is basically the temperature that requires, is the temperature that if temperature remains constant as solid turns to liquid. So when you're heating up a solid to melt it to turn into water, the temperature remains constant. And the latent heat of vaporization is the same. So when you are heating ice to gas, at one point, all of it is ice, and then at another point, half of it is water, half of it is ice, and then at one point, everything is water. And then at 100 degrees Celsius, you have liquid, and you also have the gas leaving the liquid, so you have both of them at the same time. And then after 100 degrees Celsius, it's all gas. So at 0 degrees Celsius, the latent heat, the heat of fusion is constant. The temperature is constant so that all of the ice can move from solid to liquid. And at 100 degrees Celsius, which is the heat of vaporization, temperature remains constant, so although the liquid can move to a gas. So change of state. I think you guys get the idea. So density of ice. So we're still on the state of matter, but there's a very interesting thing that you have to know about ice. Density is a measure of mass spread out over a volume. So that basically means how compact something is. So you have a, what can I use in my house? You have a dice. Well, I'll just use water. When water freezes, molecules form a structure maintained by hydrogen bonding, and we keep on seeing this word coming up: hydrogen bonding, hydrogen bonding. Solid water or ice is less dense than liquid water, and ice is less dense than water because of the orientation of the hydrogen bonds. So when we have liquid water in a cup, it looks like this. All of the molecules are just jumbled together all over the place, but kind of close together because of the hydrogen bonds. But the thing is, if I have a cup of water and I freeze the water, the structure of the water will change. Usually in a solid, the structure of the, just checking the chat. Usually when something gets solid, moves from a liquid to a solid state, it squeezes up, it gets small, it small up itself, as we would say if you're going out taxi. And so it would be condensed, But when water becomes a solid, it actually expands because it changes its structure. Anybody ever put ice in a bottle, or like your water bottle, and you fill it to the brim and then you put it in the freezer? What happens when you do that? Anybody? I'm the only one who had that incident.
It freezes and water.
Okay, one time, yes, it bursts. It bursts, or the bottle expands. But I've lost a few bottles. I didn't learn, and I lost a few bottles to, the density of ice. And so when ice is frozen, when water is frozen, I should say, it expands, which is very different from what normal liquid compounds do when they are compact. The glass broke. You see, don't fill the stuff to the brim, guys. Water expands, it will break the stuff, or burst it. Before we move to surface tension, another thing about the density of ice, when ice freezes, and for example in a pond, I put it in this, the surface is always what freezes. Has anybody ever been overseas and you go to the lake and you notice that
Yes, miss.
it's winter, the lake is frozen over, but for some reason, like the fish never die under the water?
Yes, miss.
That's because of the properties of water. The top layer of the water freezes right over, like it's tough, you can skate on it and everything. But did you know that the bottom, like inside of the pond, is not fully frozen? The water is still liquid, and the water might be a little bit colder, but it's just the right temperature for the animals to survive. So there's this icy layer on the top that
Miss,
covers the
let me tell you something, miss.
pond.
Miss.
But underneath it is liquid. The ice floats, which is also something that's unique about ice. Any other solid usually sinks. If you throw a stone in water, it sinks. I've never seen a floating stone in my life. But for some reason, when ice freezes, it doesn't sink. And it's not because water and water are friends. Ice floats in everything. I'm pretty sure ice floats in your juice.
Miss.
I'm pretty sure ice floats in your juice. I'm pretty sure ice floats in your water. Anywhere you put ice in, anytime you put ice in a liquid, ice is expected to float unless you're like have piles and piles of ice which are pushing down on one another. And you see when this ice layer forms on the top, the bottom of the liquid is much warmer, and that is also because of the specific heat capacity. That is also because of the specific heat capacity of ice. The ice layer of water. The ice layer forms a shield that blocks all the cold air from freezing the rest of the ice. Skating is harder than it thinks. So the ice layer on the top block all of that cold energy from going on down at the bottom. So nothing more can freeze. So when the top of the ice freeze off, everybody underneath the bottom good. So you ever back to the juice analogy, or anecdote story. You ever put ice in your juice and like it's just the top of your juice cool, like you're drinking the juice and you're like, whoa, you're so refreshed, and then you reach the bottom because you don't stir the juice. When you reach the bottom, the juice is just as warm as before, and you have to stir the juice in order to let the coolness of the ice go through it. That is because ice acts as a layer on top of the juice, on top of the water, and we have to stir it to get all of that icy stuff down there. But that don't happen in nature. Once the top is frozen, there's no cold air that's getting into the bottom to freeze the rest of it. So the creatures can survive. Really should have had a diagram in there, but don't worry, guys. I have a video for you. So surface tension. Any questions so far? Surface tension and capillary action. What happened to, oh, let me do this one first. Nope. All right. So water has a capacity to form intermolecular associations. And that's just two big words that mean bonds. They can attach themselves to stuff. So water has the capacity or has the ability to attach itself to stuff. Each and one stuff, basically. With molecules that share common properties, because water is polar, it will be attracted to other molecules that have charges. Does anybody remember what polar mean? One must say water is polar. What does it mean? Dun 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 dun. Dun, 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 dun. Oh, well, not exactly. Oh, I see in the chat where I can't hear. I couldn't hear. I honestly couldn't hear, but I just fixed the problem. So if you want to use the mic, you can go ahead now. I can hear you now. No, polar means that the oxygen, it has a slightly negative end, and the hydrogen has a slightly positive end. So polar, when I say polar, think about the North and the South Pole. And think that the North is like positive and the South Pole is like negative. Think of Santa Claus when I say polar, right? And think about him having to move from one place to the next in order for stuff to even out, and he goes everywhere, the bad places and the good places. So think of polar, think of Santa Claus having to go to the negative places or the bad places, and also the good places, which are the positive places. So when I say polar, think Santa Claus. He goes to the bad places and he goes to the good places, the negative and the positive places. So because water is polar, has a negative and a positive end, it can attach itself to stuff. So its polarity, or the polar nature of it, makes it itch on stuff. Think about, anybody know Velcro? Velcro? Where you usually find Velcro? You know the slippers that you can put on and you just tear it open and then put it down?
Yes.
So it attaches itself to stuff like that. So there are two properties of water that allow it to itch on itself upon anything, absolutely anything. And so there's adhesion. Adhesion is the ability of, let me go by cohesion first. Cohesion is the ability of like molecules to stick together. So water is strongly cohesive and it will form hydrogen bonds. So as you know already, water always itch on itself. Water is always sticking to itself. It's always together. Like you'll never see a single water molecule because that's not possible. But it's always in a liquid. Well, it's usually in a liquid state. So right here we're seeing the water droplets. Some are larger than some, and that's because they can come together and form larger droplets because of cohesion. So cohesion makes water droplets stick to each other in order to make a larger body of water. So if you go to the beach and you see a puddle of water, a tidal pool, and it's by itself, you ever notice that whenever the tide rises, the water will not separate itself from the other, meaning all of the water becomes one. Like you can't tell the difference between the tidal pool and the water that's coming from the ocean or the sea, because it sticks to each other. There's no separation. So if I pour one glass of water into another glass of water, as long as it looks the same, you'll never tell the difference between the two water. Pipe water and a bottle of water.
Unless you put some food coloring.
Yeah, unless you put some food coloring, you'll never know the difference because they just stick to each other. Adhesion is the ability of unlike molecules to stick to each other. So water will stick to itself, but it will also stick to other stuff. So again, we have the spider web here, and we see cohesion going on because we see the different droplets of water. And the only reason why they don't come together is because they're far apart. But if they were given the opportunity to, stick onto each other, they would. I'm pretty sure they would. They definitely would. So think about it like this. Cohesion is like the antisocial behavior of water. And that means it sticks to itself. When you think antisocial, think it sticks to itself. Cohesion is just water being antisocial. And then adhesion, is when water decides to add another person to its life, get attracted to somebody else and become social. So cohesion is the antisocial behavior of water, in a sense, but don't write that on the paper. But you can use that to remember this. And then adhesion is when water decides that it's going to be social today and go talk to some people, go mingle with other people and stick to them. Whew. Oh, then we'd have to go back to surface tension and capillary action. Any questions so far? Dun, 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 dun. I guess not. So, surface tension. So, capillary action and adhesion, the antisocial and social behaviors of water, contribute to these characteristics of water as well. So, surface tension, in surface tension, the cohesion of water explains surface tension. So the hydrogen bonding between water molecules allow liquid to resist low levels of external force. So that means that because water likes to stick to it itself, if there's a small amount of pressure that is applied or force that is applied, it's not gonna want to let go. It loves to be antisocial, so it's gonna itch upon itself and stick with it until there's a large amount of force that will separate it. So for example, the high surface tension of water makes it easier for smaller organisms to move on it. So right here we're seeing a water strider that can walk on water. Has anybody ever seen this before? I've seen this in Jamaica before.
The something lizard.
Yes, there's a lizard that walks on water as well.
Jesus Christ lizard.
Yes, that is true. It's called the Jesus Christ lizard.
I just can't remember the scientific name. Basilisk lizard. I just don't remember.
I'd have to look up that one too. I in doing my research, I saw a myriad of organisms that can actually walk on water, including the Jesus Christ lizard. And it's not blasphemy, guys. Like they call it that because it can walk on water, pretty much like Jesus did. And the water strider can do the same. So as you can see, it's like it's stepping in the water. It's like it's standing on a sponge and it's like pressing down into.
Means it has web feet that help it. Miss. Just like opens up its web feet and starts running real fast, but it can only do it for a time. So it just uses to get from one side of the river to the other.
And for the Jesus Christ lizard, they also have air bubbles on the bottom of their feet that help them to walk on the water. And I believe this does it too. But as you can see, it's obviously standing on the water. It's not floating and drowning or whatever. It's standing, but the amount of force that it's putting on the water is not allowing it to break through the water. So surface tension allows water to resist low levels of force. So we can walk on water because we're way too heavy. I mean, way too heavy, but this can walk on water. Capillary action now, over here. Capillary action is the result of adhesion and surface tension. Whoa, so everything is coming together now. So adhesion is the antisocial behavior. Cohesion helps with surface tension. Cohesion is the antisocial behavior, and adhesion is the social behavior. So adhesion and surface tension give rise to capillary action. So adhesion of water to the walls of the vessel will cause an upward force of the liquid at the edges, and thus a curve is seen. Capillary action is the movement of liquids to slide through narrow area by the attraction of molecules of liquid to the molecules of the solid. So, perfect example. When from this diagram, if you put a straw in a cup of water, you can notice that water will move up into the straw without you sucking it. It won't go all the way up. but water fills the straw because that's what water do. Water moves into empty spaces. But you'll also notice that there's a curve. There's a curve there, and that is because of adhesion. Remember, adhesion is the social behavior of water. So adhesion is going to cause the water molecules to stick to the wall and basically climb. So notice how water worked its way up the glass to beyond this original position. So the original position is the water surface. And notice how water molecules are adhered to the side of the glass. And in plants, capillary action is very important because capillary action allows for water to move through the plants and get up to where it has to go. So gravity has nothing on capillary action in plants. Gravity don't hold back water in plants at all. Like water see gravity and be like, psych. So what happens in the plants though is that water is taken up through the roots, as we stated earlier. Water the plants, ions, minerals dissolve in the soil and then are taken up. And when they're taken up, they go all the way up because of something called transpiration. Basically, water is in the leaves, and then when the sun gets really, really, really hot, the water leaves the plants. And the thing is, the cohesion of water allows water to pull on other water molecules to fill up the space. So let's think about this. We're all holding hands. In a non-COVID world, we're all holding hands, and we are playing. Oh no, not holding hands. We're playing tug of war in a non-COVID world, and one side is winning, and while they're winning, they're dragging us into the position that they were previously. So cohesion does that in plants so that water can move from the roots to the part of the plant that it needs to go. So it's a tug of war, really, but the top part of the plant is always winning. So water is always being dragged up into the plant, and this is because water is leaving the plant through the leaves. So let me go through that again. Capillary action in plants is when water is dragged up the plant because water molecules are leaving the plant through the leaves. That's called transpiration. Transpiration. Yeah. So water as a solvent. Water is a polar solvent. And a solvent is a substance.
Miss, I've done an experiment, and turns out salt does melt ice.
Salt does melt ice. Water, and I'll explain why. After this. Water is a polar solvent, and water, as a result, dissolves a lot of liquids and gases. A solvent is a substance that is able to dissolve other things. And things that can be dissolved in a solvent are called a solute. I know I just said a whole lot, but just remember, a solvent dissolves stuff. So water is a solvent. You can dissolve Kool-Aid in water, ice in water, sugar in water. What else can we dissolve in water? Drop some stuff in the chat. What else can we dissolve in water? Ladies and gents, we can dissolve ice. Well, we can dissolve sugar, salt, Kool-Aid, drink mix. Anything else? Just those four things. I mean, when I'm in the bathroom, I know that my soap dissolves in water, powder dissolves in water, my shampoo. If my shampoo never did dissolve in water, it would never leave my hair. So water helps you to wash out things because it dissolves. Yeah, let's go. So solids are said to be soluble, meaning they can dissolve in a liquid, usually water. Tissue, okay. Water solubility is a measure of the amount of solute that can dissolve in water at a specific temperature. And water's polar nature allows for the organisms to dissolve minerals in which are easily transported throughout the body. And it is used to make other chemicals, etc. So I have this video of how salt is dissolved to give you an idea of how water acts as a solvent and why water acts that way. So this video doesn't have any sound. I will describe what's happening.
Why does this have any sound?
So this video is about how salt dissolves in water. This is a creator of the video. So this is a water molecule, and the green hair puffs that I'm going to call them represent hydrogen, and the blue
Weird.
Yeah, the weird ears. You can't call them ears. I'm calling them like pom-poms.
No, miss, the weird earth. The weird earth.
Oh yes, it does kind of look like an earth with the green and the blue. And then the blue is the oxygen. Yeah. So as we can see, the oxygen is bigger than the hydrogens, which was stated before. That's what makes it slightly negative, because it's all mean and wants to take up everything because it's so big. And that's why it's negative. Press play. So here we have a salt crystal. Salt is sodium chloride. So I'll drop what sodium chloride is in the chat, so that, because this doesn't give you, sodium is an atom as well. Cl, chlorine. And when they come together, they bond just like water. They come together to form NaCl, which is called sodium chloride. Does anybody know what we use sodium chloride to do? Dun, 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 dun. Dun, 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 dun.
Put in the food.
So sodium chloride is salt. It's regular salt. We use this salt in food. We use it to kill snails. We use it to melt ice, as stated earlier. It's just the general salt that we use in our kitchen, in our household. So here's a salt crystal. The chlorine molecules are negative like the oxygen molecules. So that's something to remember. And the hydrogen molecules are positive like the sodium molecules. Atoms, sorry. The atoms of hydrogen are positive. The sodium molecules are positive. The oxygen atoms, I keep saying molecules, are negative, and the chlorine atoms are also negative. So can anybody guess what's going to happen? Opposites attract. So if the oxygen is negative and the sodium is positive, what do you think is going to happen? Opposites attract. Dun, 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 dun.
They come together?
Yes, they will come together because opposites attract. Let's see how that happens. So the oxygen is going up to the salt now, and the video is showing the polar charges of water. So you have the plus side, which are the hydrogens, and the negative side, which is the big mean oxygen. I say it's mean because it just takes up everything. charges of sodium chloride. So they're showing you that the little yellow balls, which are sodium, are positive, and the big red ball of chlorine is negative. So water goes and attaches itself to it, and here we can see the charges that are interacting. So the positive hydrogen is attaching itself to the negative, like the hydrogen is the green ball, remember that. So the green ball is attaching itself to the red ball because opposites attract. The green ball is hydrogen, is positive, and the red ball is chlorine, is negative. Opposites attract, so they are there and they're, you know, attracting. And then we have the blue ball, which is oxygen, and the yellow ball just right around here that is attracting itself to. Yeah. So when they attract each other, they pull them apart. So the positive ends of the water molecule pull away chlorine. So all the hydrogen them surround a chlorine and just drag it off. And they break off the salt, and they break off the salt at a molecular level. So they keep doing that. Opposite charge attract. Negative ends of water molecules carry away the positive. So the oxygen takes away all the sodium, which is positive, and all the hydrogen takes away all the chlorine, which is negative. And then eventually, after all of that dragging apart stuff, okay, where does it go? After, when the water molecules interact with the salt, it breaks it apart. Where does it go? It just dissolves in water. So the salt, what the water does is act as a, it acts as the thing that breaks it apart. So when you put the salt into the water, it was hard, but then when you leave it in there or when you stir it around, the water molecules begin to rip apart. You can't think of it like that. The water molecules rip apart the sodium and cause it to dissolve. And that's how things, and cause it to disappear in the water, basically. And that's how things are dissolved. So the solvent is the water, because the solvent is a thing that is a liquid, yeah, that the solute, or in this case, the salt, is broken down into. So solvent is water, and the salt is what is dissolved in the water. So whenever we see things dissolve in water, it's usually that water rips apart the whole structure. I'm putting it in that way because I think it's easier to think of when you put it in that way. Water rips it apart so that it is easier to be transported. Water rips it apart so that it is smaller. Water rips it apart for many reasons. Also, example, in our bodies, water is what makes our blood a liquid, right? If it wasn't for water, our blood would be hard. It would be hard. It wouldn't be liquid. So we wouldn't, the hard form of our blood couldn't help us. We need water to act as a river throughout our body that transports all of the things around our body. Same thing in plants. So because water is a solvent, because water is polar, it breaks apart what should have been hard blood, and we don't have hard blood in our body. I'm just giving an example. And when it does that, it makes blood travel around the body easier. So the blood is able to carry oxygen and other nutrients and white blood cells to fight off bacteria and other things that are not supposed to be in our body. Because of water, our body can function effectively because it allows things to go around our body faster. It allows things to dissolve in it and be carried from one point to another. So water is like a river, or you can think of it as a road. You can think of it as JUTC bus park. If I'm supposed to go home, I can't walk because it's too far of a distance. But if I take a bus, it makes me get where I need to go faster and yeah, on time. So yeah, the water molecule, the crystal molecules are pulled apart and dissolved. So yeah. Do I stop sharing so this goes away? Or all right, so we're back, almost done. Almost there. Can whosoever can you erase that, please? Hello, can you erase that, please? Okay, so we're almost done. Okay, so I already covered this. This is just a table of everything I share. Okay, I can do that. Let me see where I can do that. Why? Okay. Oh, I see. Thank you. Thank you so much, William. Almost done. Oh yeah, so this is like the second to last thing. Thanks, William. I disabled. So the pH of water. The pH of water has to deal with the neutral ability of water. So in chemistry, pH is a scale used to specify the acidity or basicity of an aqueous solution. And I'll explain all of those big words, what they mean. Lower pH values correspond to solutions which are more acidic in nature, while higher values correspond to solutions which are more basic in nature. At room temperature, pure water has a neutral pH of 7. That's just general knowledge. I'll explain what it means. So as you can see on the table down here, we all know what acids are. Acids are the things that burn you. Acids are not the solutions that you're supposed to mess with. So are bases, but we most likely know the acids. So stuff that are acidic include batteries. Batteries are the most acidic on this scale. Stomach acid, your stomach has acid in it. That helps to break down the food. We have lemons that we drink, vinegar that we use to clean our meat. Drew main. What does what mean? Acidic or basic? Okay, let me jump to that so that I can just explain it. So, before you say why does water have a pH of 7, bases are substances that have a high negative concentration of OH ions. And ions down here, as you can see, is an atom that loses an electron. So hydroxide is a combination of oxygen and hydrogen, and then when they come together, both of them, even though they're one unit, they lose an electron. So they come together, but then they lose an electron. I mean, it's an anion. So when they come together, they gain an electron, right? And that makes it negative. So bases have a lot of negative hydroxide, and acids have a lot of positive hydrogen ions, which have lost an electron. Yeah. So bases, how do I put this? Bases and acids, they are alike because both can be corrosive. Corrosive meaning they can damage your skin. Both can be toxic to your body, but they complement each other. Meaning, if I put an acid and a base together, they will have a reaction in order to make each other balance out the number of hydrogen and oxygen ions that they have. So oftentimes, when you put a base and an acid together, they create water and other stuff. Not water alone, but other stuff. So bases, just remember this, have OH ions or OHs, and acids have H's. And if you look, OH and H with two H's, I should say, and a single oxygen would make water. So an example of a base would be, let me go back here, would be baking soda. I was looking for a popular one that we know. Baking soda. And does anybody know that famous thing that we react baking soda with in order to make a volcano? Dun, 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 dun. Dun, 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 dun.
Miss, why do you keep on saying that? It reminds me of something, but I just can't put my tongue on it. I'm on tip of my tongue right now.
All right, so baking soda reacts with vinegar. And so vinegar is an acid and baking soda is a base. So everything that is below 7 is, so from 0 to 6 is an acid, right? And from 8 to 14 is a base, or it's known as an alkaline. So not alkaline the artist, but you can use him to remember that. Base. They're opposite. So when they react with each other, the vinegar and the baking soda, they neutralize each other. Neutralize meaning they even out each other. So for example, if you have a friend who can sing and you can dance and you guys are entering a talent competition, your talents would complement each other, and so you guys can win because you have talents that complement each other. Going back to this, so why does water have a pH of 7? So the concentration of hydrogen and hydroxide in a solution are equal in pure water. Therefore, it has a pH of 7, meaning in the base, you have a whole lot of hydroxide ions, but in the acid, you have a whole lot of hydrogen ions. So there are two different extremes. But in water, they're equal, they're balanced. You have the same amount of hydrogen overall and the same amount of oxygen, hydroxide overall. And the pH is a value of 7, and this is very important because it indicates a neutral solution. And all other substances are compared to the neutral point. So basically, this is saying water is the perfect pH. You can drink water and it don't kill you. You can bathe in water. Like anything you do with water, as long as you use it appropriately, not in excess, water basically can't kill you. I don't mean like drowning or whatever. Like water is not a substance that can kill you if you just ingest it. These other things
If it's poisoned.
Yeah, as long as it's pure
Lead
water.
poisoning.
As long as it's pure water, it can't kill you.
Lead poisoning.
But these other things can, not necessarily these examples on the screen, but there are other acids that can kill you on ingesting it, and there are other alkalines. But water has a perfect balance of hydrogen and oxygen, and because hydroxide and hydrogen, and because of that, other things can live in it, other things can dissolve in it, and hydrogen is the perfect environment to host a lot of things. Whew. And that is it. So I have this video. It's really cool. Does anybody know Amoeba Sisters? Well, Amoeba Sisters. Oh, somebody does know Amoeba Sisters. Danielle. All right. So I have an Amoeba Sisters video. It's just 6 minutes, but it's 6 minutes of fun because Amoeba Sisters, even though it's animated, even high school students like me watch Amoeba Sisters, even university students, which I am soon. I will be soon, watch Amoeba Sisters. And this is just a summary of everything that I shared earlier. And some things that I miss. So enjoy.
I can't hear anything.
You can't hear? All right, let me use
No, Miss,
YouTube.
you share your sound, Miss? Do you share your sound?
Yes, you're not sharing computer sound.
riddle. We're bad at riddles, but more like clues about our favorite molecule. It's polar, it's like an outstretched, its properties are awesome, and it makes up 3/4. So we have a riddle for you. Okay, not really we're bad at riddles, but more like clues about our So we have a riddle for you. Okay, not really a riddle. We're bad at riddles, but more like clues about our favorite molecule. It's polar, it's shaped like an outstretched V, its properties are awesome, and it makes up 3/4 of the surface of the
Is something wrong?
What is 3 plus 4?
What is 3 plus 4?